So I just emphasized a moment ago that the rings are pretty much in a single plane. And interestingly, that plane in which the rings reside is actually very thin, very, very thin. It's a large diameter, because the rings go out about 2 planetary radii or so. But if you consider the tilt of Saturn's axis, which is around 20 degrees or so, what that means is that from our point of view in the inner solar system, as Saturn orbits around, and we'll see it's many years for Saturn to do this, but as Saturn orbits around, we're going to see the rings from a different angle relative to their own plane. So, for instance, back in 1987, we're actually going to see kind of a spectacular, almost a face-on view of the rings. So 1987 was a real good year to observe Saturn, because you would see the rings kind of face-on. But as we move up to 1995, we're starting to look into the plane of the rings themselves. So in 1995, the rings virtually disappeared from view, which tells us they're very, very thin, right? If they had any thickness, then you'd sort of still see it as some kind of a thick layer. But they virtually disappeared in 1995, so they're very, very thin. Now that's a puzzle right there. Why should they be so thin? Yeah, good question. I mean, you might expect them to be kind of diffused and extended somehow. So the fact that they're so thin already suggests that there's got to be some kind of mechanism that's enforcing that thinness. So we'll talk about that a little bit later. Moving into 2003, we were seeing underneath the rings of Saturn, this is kind of the naughty time, when we're looking up under the rings there. Then we're actually now more or less entering the phase where we're going to be looking into the plane. Okay, so these are Hubble photos in 1994 and 1995, and you can see a pretty dramatic change already into 1995 in terms of our ability to see into the ring plane. We do see a couple other things showing up here. A couple of satellites, which are pretty close to Saturn, around the same radius that the rings themselves are in. And we'll see that those satellites actually play a profound role in enforcing this thinness of the rings that I was just noting a moment ago. These are moons that we call shepherd satellites of Saturn, and their own little gravitational fields, which are very weak, because these moons are actually much smaller than our moon. But nonetheless, they have enough gravity to help keep the ring particles in that plane, so it's called shepherd satellites. So here's just a time-lapse sequence going from around 1980 to 1994, roughly, as we work our way down. And so, we're seeing a different perspective from Earth, so we see different views of the ring. But again, notice that we're not seeing too much change in Saturn's atmosphere. And in particular, we don't really see any major storms like a great red spot or anything like that. All right, so I mentioned that Saturn's orbit is many years. And you could actually see that already when we looked at the numbers, 1980 to 2003. We're talking about a 25, 30-year orbit just from the photos I already showed you. So let's see if we can confirm that. Well, this time we're actually going to turn Kepler's third law around and suppose that we already know the period. So the period is about 29.5 years, consistent with what we just saw for the sequence of the ring photos. Let's suppose we know the period is 29.5 years. Now we can ask, could we compute the semi-major axis from knowledge of the period itself? And of course we can do that by taking Kepler's third law. And this is the standard form, but now what we're going to do is isolate the semi-major axis. Now this is a cubed over here, so if we want to isolate A, we must take the cube root of both sides of that equation. In other words, we raise both sides of the equation to the 1/3 power. And the way this works is if you raise something to a power to another power, then what you get is you multiply the powers together. So if we raise the right-hand side to the 1/3 power, then the resulting power of A is 3 times 1/3 is 1. Okay, so we did this because we want to isolate A. So we achieved that. Now I actually switched the sides of the equation so I have A on the left side. Now by the same law, if I take the cube root of something that's raised to the second power, then we're going to take the product of 2 and 1/3, and so the power is 2/3. That's algebra, right? So the point of this is that now, for any given period, we can pretty easily compute the semi-major axis by just raising the period, which needs to be expressed in Earth year units, because that's the way the equation is written down here. We just raise that period in Earth years to the 2/3 power. So the period for Saturn is 29.5 years. We raise that to the 2/3 power, and we get about 9.5 astronomical units, which is exactly what we already saw. That was the correct distance in the table. So again, just to emphasize that Kepler's third law keeps on working. It's the Energizer bunny of the Kepler's laws. It just keeps on working. Actually, it also keeps on working all the way out into the outer solar system. Just one final point about Saturn's orbit. Pretty low eccentricity, about 5%. So that means there's about a 10% variation in distance from the Sun as we watch Saturn orbit around the Sun. 10% variation. Perihelion distance is about 9 astronomical units. Aphelion 10 astronomical units. So there's a 10% variation. This is an outer planet, like Mars and Jupiter. It's going to be easiest to observe during what we call a favorable opposition. So remember that the meaning of opposition here is that Saturn is opposed from the Sun, from the opposite direction from the Sun. So that's what we mean by opposition. And when we say favorable opposition, that means it's an opposition which occurs when Saturn is at perihelion. Because when it's at perihelion, then the Saturn-Sun distance is 9 astronomical units. We subtract 1 astronomical unit for the Earth-Sun distance, and so the bottom line is that the minimum Earth-Saturn distance is then 8 astronomical units, and that occurs during an opposition that happens when Saturn is at perihelion. That's what we mean by a favorable opposition. It's an opposition that occurs when the planet is perihelion. So if it was sort of an unfavorable opposition, that would be an opposition that occurs when Saturn is farthest from the Sun. It would still be on the same side over here as the Earth. But in that case, what you would do is you'd take 10 astronomical units and subtract 1, and so your distance would be 9. So, at an unfavorable opposition, the distance between Earth and Saturn would be 9 astronomical units. So obviously 8 is better, it's a smaller distance. So that would be the most favorable time to observe Saturn. And of course, we have the standard reasons why that's true. One is that Saturn is obviously just simply closer to the Earth, so it's going to look larger in angular terms. But the other thing is that Saturn is at perihelion, which means it's closest to the Sun, which means it's a little brighter in terms of reflecting sunlight. Okay, so all these outer planets are best to observe during favorable opposition for these reasons that I just stated. We have the minimum distance from the Earth, the minimum distance from the Sun, and therefore the largest angular size. All right, so to talk about Saturn's structure, we want to compute this density. Now, we already know the density is less than 1 gram per cubic centimeter, but as usual, I'll go through this whole formula here. The radius is 60,000 kilometers. So that's, I remember Earth's radius is around 6,000 kilometers, so there's your 9.4 or 9.5 ratio there for the size of Saturn compared to the size of the Earth. And the mass in grams is 5.6 times 10 to the 29, sorry, compared to Earth's mass, which is a few times 10 to the 27. So this is why you get this factor of 100 for the mass of Saturn compared to the mass of the Earth. The volume of Saturn is around 10 to the 30th cubic centimeters, according to our standard formula for a sphere. You might think that because of its rapid rotation, it might be a very oval shape, but sphere not. Sphere not. It's actually a pretty spherical. I'm sorry, that was spontaneous. It never would have worked if I had reversed it, but those things only work if they're spontaneous. Sphere not, yes, we can do this calculation by using the spherical formula, and what we get is indeed the density that I already showed you in the table. An amazingly low density for a planet. This is actually comparable to the Sun's density. The Sun's also completely gaseous, but now, of course, we're talking about Saturn, not the Sun. So, as usual, we can make some basic conclusions from this one single number, which is the most powerful single number that you can use to figure something out about a planet. From that number, we can conclude that there's practically no iron, practically no really dense core. Could be a little bit of rocky material, but probably not very much. And in fact, Saturn is composed mostly of hydrogen gas. It's a very relatively small core. So what we would say is that the hydrogen composition is probably similar to Jupiter, but it has less of a core. And that's why its density has gone down. Oh, this is interesting. I forgot about this. This is sort of a Club Med survivor thing going on here. Okay, right. Oh yeah, this is, yeah, the idea here is the density is around the density of water. So they're not going to sink too fast. Jupiter's going to sink a little bit because it has a density of about 1.2 grams per cubic centimeter. And then this is actually, he's afraid of getting his rings wet. There's actually a Latin term for that, ring phobia, which I don't remember offhand, but there's a phobia of getting your rings wet. Anyway, but the difference is that Saturn actually would float, and of course, ironically, Jupiter is smoking the cigar, which is going to be put out, right? Saturn was, there'd be a chance it would float, but very unhealthy habit, even for planets, by the way, I would say. But again, the point there is just to emphasize that Saturn's density is so low, it actually would float. If you could put it in a gigantic ocean, because it's got less than 1 gram per cubic centimeter of density. Now, when we look at these giant planets, like Jupiter and Saturn, what we're seeing, to some extent, is multicolored cloud tops. We saw that more dramatically when we look at Jupiter, but even Saturn does have color variations. You see different shades of yellow and white. And it turns out that when we look at little clouds and storms and things that are moving around the planet as it spins, we can compute the period of spin of the planet. You know, how fast it's actually spinning. Now, if it was spinning as a solid body like the Earth is, you know, you could look at the continent of Australia spinning around, or you could look at the continent of North America, you just look at the same spin period, 24 hours. But it turns out that when we look at different latitudes on Saturn, or even on Jupiter, what we actually see are clouds that move around with somewhat different periods. So it's not rotating as a solid body. It's not really too surprising because we know that it's gaseous anyway. I mean, it isn't actually a solid body. But even as a gaseous planet, it could be rotating with the same period at all latitudes. But it isn't. It's displaying this phenomenon we call differential rotation, which is a rotation period that's different at different latitudes on the planet. So what we see when we look at the core, well, the magnetic field actually allows us to deduce what the deeper spin period of the planet actually is, because the magnetic field is anchored into the core or the sort of metallic hydrogen region of the planet. So the magnetic field, with a period of about 10 hours, similar to Jupiter's spin period, is actually the best way for us to really determine what the spin period of one of these gas giant planets is. It's the magnetic field. I think I asked about that on the next exam. Note about that. So we don't use the cloud tops. Instead, we use observations of the magnetic field to deduce what the spin period actually is. And by the way, 10 hours is incredibly short for a gigantic planet like this, spinning in only 10 hours. In half the time it takes Earth to spin. Now, this object's 10 times larger in diameter, but it's spinning about 2.5 times faster. Now, if you remember that Earth has this Coriolis force we talk about, when blobs in the atmosphere change latitude, there's a strong tendency for them to arc to the right, remember, the Coriolis effect? Well, with only a 10-hour rotation period, combined with the larger size, that means that there's a much stronger Coriolis force on Saturn, and also on Jupiter, for that matter. And that fast rotation is going to drive these powerful winds and storms and streaming types of oceans and cloud tops.